Quiet, guys.
Oh, I know she's skinny.
Alright, we're going to do lenses instead of mirrors today, so it's kind of the same idea. Only thing that changes is a virtual image, like with a lens, you're looking at something, you're looking through the lens at it. So a virtual image appears the same side as the object, and a real image appears over here, opposite side of the object. Does that make sense to everybody? It's kind of backwards. And instead of reflecting off them, since they're lens, the light actually goes through it. So, but the lines are essentially the same. They should make sense to you. First line, we draw a parallel, and then it goes through the focal point on the other side. Does that make sense? The second one goes through the focal point, and then parallel. And the third one we can draw just goes straight through the center of the lens. Does that make sense, everybody? Shh, quiet. Okay. So for this one, first one we'll draw parallel, and then through the focal point.
Does it go all the way to the center line?
Goes all the way to the center line. I do a great job drawing that. Hey guys, this is a converging lens. So a converging lens is one that focuses all parallel light rays that are coming in on the focal point right there. So on F. When you see 2F, that means it's the same as C. It's the center of curvature. And the center of curvature for these, if you took like this side and made a big giant circle, the center of that circle would be at C or 2F. And same for this side. Everybody, any questions on that first line? Okay. The other one we can draw.
What is the 2F?
2F is the center of curvature, so it's the same thing as C. C is always like 2 times the distance from F, so that's why it's 2F. I'm going to draw 3 lines for this one because it'll be slightly useful later. We can also draw one that goes just directly through the center of the mirror, and it just keeps going. So it goes like this. That's through the center of the lens, I'm sorry. So it just goes straight through, and it's at the center.
Would that be a different color?
You can draw this a different color. You guys can color code this however you see fit. Alright, so our image actually forms right there, kind of a tiny arrow. The other one we can draw goes, I'm going to draw a third one here just so you guys see them all. Goes through the focal point on this side, and then goes directly over. So you see how all 3 of them intersect at the same place? And that's where the image forms. So it doesn't matter which 2 of those lines you draw, you just have to pick 2 of them. Okay, this is like a lens like in your glasses, for example. And so your eye is like over here. I'll draw a bad eye. So you're looking through the lens, and this tells you where the image forms. Because it's on this side, you can't actually, like if you're looking through it, it would be blurry. It's a real image. It has to be projected onto a sheet of paper, like onto a screen of some kind. Alright. Those are the light rays. So the light's bouncing off whatever the object is here. And these are just sample light rays to figure out where the image is. Okay. Alright. So, what are the characteristics of this image?
Real.
Real.
Inverted.
Inverted. Smaller. Alright. So whenever you have an object past the center of curvature for a converging lens, one that focuses light, it is always real, inverted, and smaller for the image. So whenever it's past C or 2F, it's going to be real, inverted, and smaller. Questions about this one? Sarah?
So like, how do you just know that those 3 go together, or did you know like which side is which? Like 2F?
You always start with the wherever the first arrow is. So the arrow that was with it was on this side, so that's where we started. Does that answer your question?
Yeah.
Alright. Let me erase this, we'll do the next one.
you know, it's in front of or behind the mirror.
This is a lens.
That's this is not.
So like with a lens, your eye is always
That was the real and like virtual.
so your eye is always over here with the lens. So like if you're looking through the lens at the image. Does that make sense?
And
So
how's
that's
it real? It's like
If it's real if it's on the same side as your eye, essentially. It's virtual if it's over here. So if you guys, so a virtual image in a lens is like what you normally see when you like look through something. So Ryan has his glasses on. When he looks through those lenses to see something, he's seeing you guys as a virtual image because it appears behind the lens. When I did you remember when I did the magnifying glass and projected onto the paper? That would be over here. So that would be over here, so that would be a real image. Chloe?
When did they come up with that though? Because wouldn't you think that seeing something through it, like where it actually is, would be real, whereas something that's coming back at you that's not really there would be virtual?
So like, what they mean when they say real image, it's an image that has to be projected onto something you can like touch. So the image is in the real world. A virtual image, like with a mirror, is in, for lack of a better word, like the mirror world. Like to touch your image in a virtual image, you have to reach through the mirror.
So is that why in his glasses, even though I could touch something out here, he can't go through
Yeah.
his glasses and touch it?
Kind of the same idea. It really has more to do with mirrors, like the real virtual image,
Yeah.
but it goes for lenses too.
Okay.
Okay, so this one, guys, do you remember what happened when we had it on C with a concave mirror?
It's just under it. Same size.
Same size. This time it's going to be the opposite side though. So it's going to go, see how well I can draw this. It should end up right here in the same size. Remember it's at the center of curvature on this. It's going to be the same size and upside down. So we go there. And then do that. Nope, that's not right. Wrong place to draw through. Goes through F, not 2F. And then, do you guys like drawing it through the center, or would you rather draw it through F and then over straight? Okay. Yes, it's a strong opinion.
Like, stop. Whoa.
Yeah, I'm off a little bit again here.
It's okay.
But it should be the same size and at 2F, or at C. It's hard to draw these perfect,
Wait.
especially with the meters. What?
I drew one from 2F through the center. Is that a way to do it too?
Yeah, so you can also draw like from there to the center. And it comes to the same spot, or approximately the same spot. Any questions on this one?
I just don't know.
Go on.
Do you have to draw that bottom line? And if so, what's that?
You only need 2 of the lines. So I just drew all 3 just in case it's easier for you to draw one than the other. Alright,
Mr. Kenta,
yes.
I'm just confused because like on the last one, wasn't our first line straight through? Are they all going the same?
So you can always, like, the first one I drew is parallel and then goes through this focal point on the other side.
Okay. So one line goes parallel then through the circle?
Yep, the other line goes through the focal, then parallel. This line just goes straight through. So you can draw 2 of those 3 lines to get where the image is. Any questions about that? Alright, what are the characteristics of this image? Real?
It's the same.
So real, inverted, and the same. So anytime it's at the center of curvature, it's going to be real, inverted, and the same size.
Where the eyeball is on the board, is that?
That'd be like, that's where you assume your eye is, essentially.
Okay.
Does that
I
make
just wanted
sense?
to make sure like that was right and you just didn't keep it up there by accident. Okay.
So we always assume you're looking through a lens even if you're like looking behind it or something like that.
Okay.
Okay, can I erase this? Alright. Number 3 is between the center of curvature and the focal point. What do you think it's going to do? Like based on the ones we did yesterday.
You need a figure.
It's gonna be, you think it's going to be bigger, real or virtual?
Real.
Real,
And inverted.
inverted. So let's see what happens. So we go straight
Then through focal.
and through focal. Any questions on that line? And then we go through focal. And straight. So our image forms right here.
Ah.
So what is that one?
It was funny. It was.
Real.
Inverted. I laughed.
What does
Yeah.
inverted mean again?
Upside down. So this arrow is pointing up, the
Oh,
other is
yeah.
pointing down. It's not real virtual. Real.
What is an example of a converging lens in the real world?
A magnifying glass.
They're usually upside down.
Usually when you use a magnifying glass, you're doing the next case. Does that make sense?
How do we know, what are we comparing the size to, like big or small?
The original one. You see that
Oh,
small?
the line,
It's
the
bigger.
line length,
So anytime it's between the center of curvature and the focal point, it's going to be real, inverted, and larger.
okay. But how do you,
Is that right, Brian?
how do you, it's like, aren't everyone's drawings gonna be kind of different and like,
Everyone's drawings are going to be
so
kind of
large
different.
and small?
Shh, guys, quiet, Michael. Everybody's drawings are going to be a little different, but you see how, like, even if you had it, like, 75% as big, it's still bigger than the other one.
Okay.
And, again, if it's between these two, Ellie,
Uh-huh,
these 3 things are always true.
okay.
So, like, you can probably figure out the answer before you actually get to the, doing the problem. Alright. And actually, a good example of this, like I said, a converging lens is a magnifying glass. So if you look at a magnifying glass at something close, you can actually see it. If you look at something far away, it's blurry through the magnifying glass. Does that make sense? Okay, can I erase this one? Alright, one thing I didn't put on this one because it's the same as before. What do you think happens if we actually had the object on the focal point? You don't need to write this down. You probably no image. So if the object was on the focal point of this converging lens, there'd be no image formed because the rays would be parallel. Does that make sense to everybody? Alright, so this one. This is the normal thing. If you use a magnifying glass, this is going to end up being a virtual image, just like before. Alright, so we go parallel, do the focal point, and now we've got a choice here. We can't go through this other focal point, can we? What do we want to do if we wanted to use that? We'd go like it's coming from that focal point.
Yeah.
So we'd go like that, and then horizontal. And the other line we can do, I'm going to draw the third one up here too, is just straight through the center of the lens. So like that. So do those 3 lines ever intersect on that side? No. So what kind of image is it going to be? Virtual, so we have to trace it back. Let's start with this one. So they meet right here. So that's where our image forms.
Wait, the one that's right now is horizontal, the dashes that you drew, wouldn't that kind of be at the angle because the line that's coming off of it went to focal then horizontal? You just made it straight horizontal.
Which one? This one?
That one, yes.
Yeah, it should be straight horizontal.
But how come because it curves up then goes horizontal? Shouldn't it match with the little curve up where it goes to the focal point?
This line right here,
Yeah.
you draw that like it's coming from this focal point over here.
Yeah, but shouldn't the little dotted line extend from there? Because that's like
No, you're always tracing back the
horizontal.
ray that got bent.
Okay.
So whatever ray is coming out of, you're looking for either where these ones on this side intersect, or where they intersect if you trace them back.
Okay.
Does that make sense? And if we did this one, we'd get approximately the same spot. So again, if I drew it perfectly, it would work out perfect. Okay, so what is this one? Virtual.
Bigger.
Upright.
Upright.
And this is why when you're using magnifying glass on something, the object appears bigger. Make sense?
Yep.
So you're looking through the lens and you see it as bigger than it should be.
Is that why it only works that way if you like have it in the right spot? 'Cause,
Yeah.
like, I think if you hold it back, it does flip it over upside down. Okay.
So like, if you're to use a magnifying glass correctly, you have to be close to the what you're actually trying to magnify.
For it to work.
If you pull it back, like if I tried to look at Brian through a magnifying glass, the image wouldn't appear right. He'd appear like blurry and stuff like that. Make sense?
What? Draw this next line.
All right. Last one. We do have something else to do, guys. So don't get too excited. What? You haven't been doing anything anyway. All right. So this one I only have one drawing because just like a convex lens, there's only one thing that ever happens with diverging lenses. So this is a diverging lens. So instead of focusing light in one point, it spreads all the parallel rays out, so it looks like it's coming from this focal point. Does that kind of make sense? Lines we draw are still the same though. So we go from there over, and then, but instead of going through this focal point, we draw it like it's coming from this one.
Oh, okay.
Does that make sense, everybody?
I messed up.
What did you go
That's
through on
done.
What?
How do we know to do
the,
that?
what did you like go through?
Okay, so for a parallel ray with this kind of lens, it doesn't focus onto a point, it spreads out from a point. And so it can't spread out from this point, so it's gonna spread out from this one back here. So we line up on that focal point where it met the lens there, and that's where it spreads out from. Does everybody understand how I get that first line? Okay. Now, we can draw it, we can go focal point parallel. It's a little easier to remember. Like, this is, like if you're gonna mess up one of these up, it's gonna be on this one, because the other one I think is kind of straightforward. This one I would suggest at least to check your work. If you want to draw the other one, I'll draw it here in a second. Is you go just straight through. That's when you can always do it. It's kind of easy to do, especially for these diverging lenses. Do these two rays ever meet over here? No. So this one we don't need to trace back since it's already on both sides, so we could trace it back over here, but just as straight, so it doesn't matter. So we'll trace this one back. And so we get a little tiny image right there.
Mr. Temple,
Yes.
when, like how that one we went horizontal, no we went focal, horizontal then focal.
Focal, yep.
When we go focal then horizontal, how do we know whether to do like the first F in front or like the second one?
You usually want to do, you can actually do either, but the way I've done it is you go, this one we want to do focal on this side. Previously we did focal like we did there and then straight through the focal on the other side, but since this is diverging we do everything backwards kind of. Does that make sense?
Kind of.
Let me draw a couple more lines up here and I'll see if I can answer your question. So, for the other one, we're going to go like this. So this is the focal then parallel, so we draw toward the focal on the other side. And then parallel.
Wait. Mikey. Hey guys.
Wait,
Okay.
I thought the focal point though is the F.
Focal points are the F. So guys, again what I did here, I drew this line toward that F, and when I got to the lens it went parallel, so if I trace this back, it still meets in the same spot.
Do you need that line too?
What?
Do you need that?
You only need two of these.
Wait, what'd you just do?
Okay.
What?
Alright, let me explain this again. So you can always draw 3 lines for these.
Right.
For the previous ones, we'd always go through we'd go parallel through the focal point on the right side. This one we did parallel and then from the focal point on the left. Does that make sense? And for the other one we did toward the focal point on this side and then parallel. So we use the opposite focal points we used before. Does that make sense?
I don't get why we had to draw the other line because I thought we already had the answer.
We did already have the answer. I just wanted to draw it so like,
Oh, I get it. Okay, but never mind.
Okay. Do you guys feel like you could draw one like this?
Can? Yes.
Okay. Alright. So what is this image?
Virtual.
Virtual smaller print.
Yeah.
Alright, so anytime you have a diverging lens when it spreads light out, the image is going to be virtual, smaller, and upright. No matter what. No matter where it is on that line. It's always virtual, smaller, and upright. Same with a convex mirror. It's always virtual, smaller, and upright in a convex mirror. So I always kind of like, in my mind, converging lenses and concave mirrors are kind of the same thing because they focus light at one point. And diverging lenses and convex mirrors are kind of the same thing because they spread the light out. Does everybody understand that? And they have similar properties at both places. Okay. Where did I put the other sheet? No, we get it later today. Don't worry.
I know, we usually got 24.
Then you usually get it at 26.
27.
Oh, just
22.
kidding.
We got 27 today. Oh, 22.
So it's 30.
I've heard like 3 different answers.
It's 30
37.
something.
We got 127.
We got
We only
like
got out
35.
34.
Yeah.
It's
We
20.
got out 127. I don't even want to. Yeah, we don't get out 127. That's a lie. Don't keep.
No, no, yeah, you're right. It's 127.
I am. What can I say?
Why do you want to be out of class, Mike?
I don't talk out of every class because it gets me to 305. Thanks, Michael. We're doing physics today. Oh, that's way all your chances. Hey, Mike, is that play that? All these are doing physics. And that's bad. Laura. I mean, psychology. You're literally gonna get like 10 minutes on this. Hey, I need like no battery. I didn't understand a word you said.
Okay.
You said your thing wrong.
Huh? Alright. So I want to at least get through the what all the equations mean here, and if we don't get to them today, that's okay. We'll probably get like 1 or 2 problems. Alright. So for C equals F lambda, anybody know what C is?
Speed of light.
Speed of light.
E equals MC
Shh. And what is the speed of light in a vacuum is what we're going to usually use here.
-8. I know.
Why would it be the name?
I'm just kidding myself.
Okay, 3.0 times 10 to the 8th. Anybody know what that is in miles per second?
A lot.
186,000 miles per second.
I said 15 trillion.
Okay, F is frequency,
Oh.
and that's in hertz. And wavelength is lambda in meters. Questions about that? Okay. An equation I didn't write down that I forgot to put on there that I want you guys to have is N, so write this equation, equals C over V. N is the index of refraction. And the index of refraction, it's unitless. It's just a ratio of how fast something moves in a certain material to how fast it moves in a vacuum. So again, this is speed of light in a vacuum. When it goes to anything else, it's going to slow down. And N is just a measure of how much it slows down.
Will it never be less than 1?
It will never be less than 1. So C is still speed of light. V is and that's in meters per second. So you can also see that the units cancel out, so that when C is in meters per second, this is in meters per second. So that's why velocity is going to be, or index of refraction is going to be unitless. So like Michael said, it can never, index of refraction can never be less than 1 because it always slows down in a different material. Alright, next one is Snell's law. That's how light bends when it changes material. Remember I talked about the fish in the water, or like why your legs look short in the water? That's due to refraction. And this is how you can actually figure out where something is, like specifically. So, I'm going to draw a diagram here just so you can remember. If you remember what that that dotted line is called? Normal line. So if it was like going from air to water, you'd have, this would be N1, and that's the index of refraction of air, and N2 would be the index of refraction of water. So all the 1s are what it's coming from, all the 2s are what it's going into. So this would bend toward the normal. So that angle measured from the normal would be theta 2. This one would be theta 1. So theta 1 is called the angle of incidence, the angle it's coming in at. Theta 2 is the angle of refraction, the angle it gets bent to. Should be indices. Indices of refraction. Angle of theta 1 is the angle of incidence, the angle it comes in at, measured from the normal, and that's in degrees, and theta 2, angle of refraction.
The plural of index.
If I write indexes, I suppose that'd be okay.
Oh, that's what it is.
So I just said.
That wasn't funny, Brian. I'm trying to learn today. Alright.
Anybody have any question?
Theta 2.
What?
Bottom one.
Yes.
Just making sure.
Oh, yes, theta 2. Thank you. So if you look at that equation, you can figure out if it's going to bend toward or away from the normal. Based on like whether it's going to be bigger, and we'll talk about that maybe when we get to the math here when we're not time. last equation is for total internal reflection. So if it's going, say it's going from N1 to N2 this time, from water to air, at some angle, instead of going out and bending, it's going to just reflect. And that angle is called the critical angle. So theta C is called the critical angle. And that's where, instead of going like from water to air and bending, it just stays in the water and gets reflected. Kyle?
So N1 is not always the air.
N1 is not always the air. N1 is always what it starts in. N2 is always what it goes to. Any questions on these?
Sorry.
Alright, there, Ryan. Alright, a couple other things to write down. So we have a couple more. Alright, so if all of these are going to be for wavelength and stuff like that for this equation, or for the first equation, are going to be in nanometers or micrometers. So, and you need it in meters, so to go from nanometers to meters, you divide by 10 to the 9th. To go from micrometers to meters, you divide by 10 to the 6th. Anybody have any questions? Alright, we'll just stop there for today.
I have one question.
Yes, Kyle?
For the critical angle, critical angle, do you add both sides or just one side?
Do you add what?
Do you add like both, like the side that goes up and then comes back down?
No, it's just, the critical angle is just this angle right here. This angle right here will be equal to it, but you don't do anything with that in the equation.